Hello everyone, welcome to this video. In this video, we'll be proving that factor groups are really groups. So in the last video, I left you with a question that the question group which is formed from the group of integers taking 4z as the normal subgroup of 8. So this factor group, is it really a group? So the answer is yes. And in fact, we can create a Kelly table for this. Let's see how. So we already know that we had four distinct cosets for this particular group, right? In the group of integers. Then the Kelly table would be this. You can verify this thing, that how it forms a Kelly table. Now, if we are able to construct a Kelly table, that means we have the identity here. The identity is this one, 0 plus 4z. And for each element, we have an inverse. The inverse of 0 plus 4z is itself, right? What is the inverse of 1 plus 4z? It is equal to 3 plus 4z, right? The inverse of 2 plus 4z is 2 plus 4z only, and the inverse of 3 plus 4z is 1 plus 4z, right? So all the inverses are there. We have the identity, we also have the associativity and the closure property, hence this forms a group, right? So here you can also notice that this question group is nothing but this the addition modulo 4 group, right? So this is also a finite group. So after having a look at this particular example, you can now say that we can define it generally for any such groups. If we take any group of integers, right, under the operation of addition, and then we construct or take a normal subgroup nz of 8, then using this we can create a question group out of 8z nz, and this would be isomorphic to addition modulo n group, in the group of integers under addition modulo n, correct? So for any n, we can construct first of all nz. It would be this set which would be normal in z, and this would be isomorphic to zn, right? This is the general group. Now let's have a look at the theorem. And in general, can we say anything about it? So the answer is yes. If we suppose G to be some group and H to be the normal subgroup of this group G, then G oblique H would be a group. This would be a group of all the cosets, and the operation would be when you multiply or compose these two cosets. So this is not just the multiplication of cosets, we are multiplying these coset representatives together and forming another coset, right? So first of all, in order to show that this forms a group, what we need to do, we first of all prove that whatever is this operation, this is a well-defined operation, right? So in order to prove this as a well-defined operation, we will show that this correspondence, that means we are taking one element from this quotient group, another element is also being taken from the same quotient group, and we are mapping it to some other coset which is also a member of this quotient group, right? So we have to prove that whatever is the operation taken from these sets, that actually forms a function. So for that, what we need to prove that if we take some element a dash, b dash from the group G, then corresponding to these elements, if we have AH is equal to A dash H, and if we have BH is equal to B dash H, so that means we have two cosets which are equal to each other for A, and for B also we have two cosets which are equal to each other. Then we need to verify that these two cosets, they are equal to A dash H and B dash H also, right? So that means by definition, what would this become? It would become ABH, and by definition, what would it be? It would be A dash B dash H, right? So we will prove that the definition of multiplication here depends on the cosets AH and BH and not on the coset representatives A and B, right? So we will prove that ABH is equal to A dash B dash H. So how we can do that? By proving this, we will be proving that the given function is well defined. So because we are given this thing AH is equal to A dash H and BH is equal to B dash H, right? So in that case, we can define A dash to be A into H1, right? A dash to be A into H1, where H1 is a member from H, capital H subgroup, and we can define B dash is equal to B into some member from H. Let's call that member to be H2, right? So once we define these two things, what would be, let's start from here and reach here. So what would be A dash B dash H? Let's have a look here. So when you start with A dash B dash H, it would be, by definition, the definition for A dash is this AH1 and for B dash it is BH2. So we can substitute it here, and next we have to perform certain operations. So here you can see we can use the associative property here, and what would be H2H? Now you know H2 is some member of H, so in that case H2H would be equal to H using the properties of cosets, right? So you have H here. Now again what we can do, we can apply the property of normal subgroup here for H, because H is a normal subgroup. So for this, the left coset would be equal to the right coset, hence BH would be equal to HB here, because H here is normal, correct? Okay, next we can apply the associative property here onto this element H1 of capital H. So because H, small h1 is a member of H, this would imply H1H is equal to H, right, using the properties of coset. So we have H here. Again we can use the associative property, and using this thing here, using the property of H to be normal, we have this to be BH. So we started with A dash B dash H and we ended at ABH, and this is what we wanted to prove here in order to prove that we have a well-defined function, right? So we wanted to prove this thing in order to prove that it is well defined. So our function here is well defined. Now in order to prove that this forms a group, we need to find an identity element. We find the inverse of each one, and we also need to get the associativity here. So identity is present because E is obviously present in H, where H is a normal subgroup. Hence EH would be the coset such that you have this as the identity of this quotient group, right? Why? Because if you take some coset and then you compose it or multiply it with EH, you would get back again AH, correct? So, and moreover A inverse H, if you take any element A from G, A inverse would surely be there, and if you construct AH, the coset from this element H, then A inverse H would serve as, this coset would serve as the inverse of this particular coset. Now we are not talking about the coset representatives here, we are talking about the cosets itself, right? So this forms the inverse, and we can also check the associativity. This is very simple, right? We can first of all apply the definition here onto these two, then we can apply it onto these two cosets, so that we have this. Now we can apply the associativity here onto the elements A, B, C, because all the three elements A, B, C, they are member of G, and G is a group, right? Using this thing here, again using the definition, we can open up on these two elements, so it would be AH, BCH. Then again on to this we can apply the definition, so it would become BHCH. So this is what we wanted to prove here for associativity, hence this forms a group, right? Moreover, the converse here is also true in this particular case. That means if we say that the correspondence AHBH is equal to ABH, if this defines a group operation on a set of left cosets of H in G, then that particular subgroup would be a normal subgroup in G. And this is what we wanted to prove here. So I hope you understood the proof well. Well, that is it for this video. Thank you for watching.